Hey everyone, today we are going to start the vector quantized variational autoencoder. This architecture is especially important for a lot of my personal research in speech processing and stuff like that, because we use these VQVAEs everywhere. It's also just as important in a lot of the different generative models. Some models that come to mind is Stable Diffusion has a variant using a VQVAE encoder. There's VQGAN. There's this whole concept of quantized embeddings come up all over the place. So the prerequisite to this is, of course, you already know what an autoencoder is, and you already know what a variational autoencoder is. So if you don't know what those are, I already have videos for both of those things. So please go watch those first. But assuming you kind of know these things already, let's just start to talk about exactly what is vector quantization, why do we care about it, and how do we implement it, and some of the limitations or problems that come with trying to apply quantization in our models. And so first, if you know what K-means is, the K-means clustering algorithm, you already know what quantization is, right? The entire purpose of quantization is to use a couple of numbers to represent lots of different numbers. And this happens all the time in signal processing, for example. In the real world, let's say you're a musician, so you're recording some audio with a microphone. In the real world, the audio that you're recording is the original audio. The source is a continuous signal, right? It's air pressure. It's just air pressure, right? It's continuous air pressure, a measurement of the air pressure. And then that air pressure hits the microphone, and then the microphone converts that analog signal, right, the continuous real-world signal, to a digital one, which means it needs to represent it in some type of floating point precision, because typical floating point precision, like FP32, FP64, they can't represent every single number. They just represent a lot of different numbers. And so quantization is kind of like rounding, right? It's basically like rounding something to the closest representation of that thing that we have. And K-means clustering is a good example of this, right? So if you look at this figure, right, we have all of this data and we've identified these clusters. And what this means is we're representing everything in this red region, and everything in the red region is it's a continuous region, right? You can pick, there's infinitely many points in the red region, but all of those points get mapped to this single center, right? Our single cluster center. Similarly, everything in the purple region, which is, there can be infinitely many points in that purple region, all get mapped to this cluster center. So this whole finding the cluster centers is an example of quantization. You're taking continuous data and representing it by your kind of discrete set of values, which is awesome. Now, the quantization, there are a couple kind of nuances that come to it. One of them is, for example, in signal processing, or if you work in audio or video, you've probably heard of bit depth, right? Bit depth is how much information you can actually represent. So if we're taking, for example, a black to white, a grayscale image, right? If you have 1 bit, that means you can only represent 0 or 1, which means you can represent perfectly black or perfectly white. But that would obviously be a very blotchy image. You couldn't have any kind of gradient between the transitions between the black and white portions of that image. As you increase the bit depth, you end up getting more gradient. And 8-bit is typically what we work with. So if you followed any of my image tutorials, or if you've trained a convolutional neural network, for example, you're working with 8-bit images, because all of the pixel values are between 0 and 255, right? For the 256 or 2 to the power 8 bits that you can represent. And the quality of a signal is directly dependent on the bit depth, the number of numbers we use to represent our signal. In the same way, when we quantize our neural network, which we'll see, when we quantize the embeddings of our neural network, I don't want you to get it confused. There is something called quantization. That's more for efficient training and inferencing. That's literally, it's called weight quantization. We're not talking about that. We're talking about basically embedding quantization. So just to make sure, because there's a little overlap there in terminology. But when we're quantizing it down, the more quantized embeddings I have available, the richer a representation I can encode in that quantized space. And that's basically the key idea, right? The more bits you have, the more information you can encode. And what we want is to use the least amount of information possible to save our data. And there's a lot of really important reasons for this, and we'll kind of explore a couple of them at the end. So yes, the vector quantized variational autoencoder looks exactly like this. So if you again remember, let's do a little bit of a recap on stuff we've seen. What was an autoencoder? An autoencoder is something that takes a picture. Let's say here's a picture of a happy face, and it encodes your data down to some vector, right? Some vector, some compressed representation of the image. And then your decoder takes this and decompresses it back to the original image, right? So you have your encoder and your decoder. And that was our kind of vanilla autoencoder. And that's it. After we did the autoencoder, we moved on to the variational autoencoder, which added one key difference over the original autoencoder. And that was basically, if we look at our variational autoencoder, again, we have a picture of a happy face. We have our encoder. But now, instead of predicting compressing our data down directly, we are going to predict some mean and standard deviation and use this to sample some z, which comes from some normal distribution of mean and sigma. And then this sampled z is going to go to our decoder to again reconstruct our image, right? Decoder. So the variational autoencoder, the entire purpose is we want our latent space z to be a Gaussian distribution, right? So we're mapping to a Gaussian distribution. So that's the key difference between an autoencoder and a variational encoder. In an autoencoder, we just compress our data down. In the variational encoder, we compress it down to a Gaussian latent space, or we're sampling from a Gaussian latent space. Again, if you want more details, just go look at some of those older videos that I'll post below, and I'll put in one of the cards above. What is a vector quantized variational encoder? Well, it's exactly the same thing, except instead of mapping to a Gaussian distribution, we'll be mapping to something known as a discrete distribution. So discrete distribution, which is called, basically it's represented by a codebook. It'll look kind of like this. So what we're going to do is we're going to have our picture, happy face, and we're going to encode our data down, just like we did, to some vector, right? We have some vector here. Let's draw a little bit better. There we go. And what we're going to have is on the side, right over here, on the side, we're going to have something known as the codebook. And the codebook is basically a couple things. The first thing is we have the number of entries, right? So how many codes do I have in the codebook? So these are kind of vectors like this, right? Dot, dot, dot. How many codes we have. And what we're going to do, and of course this dimension will be some, let's call it, I don't know, let's call it j, right? This is a j by number of entries matrix. And let's say this dimension here is j as well, but this is just one, right? It's one vector with j embeddings in it. And what we're going to do is a pairwise distance metric, right? So typically we can use mean squared error. We can use really any kind of distance metric we want, but what we're going to do is compute what is the distance between this code here and the first one. And then we're going to compute what is the distance between this code here and the second one, this code here and the third one, dot, dot, dot. So we're going to compute these distances and end up with kind of a distance matrix, right? We'll have D1, D2, D3, dot, 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 right? So we'll get the distance between this code and all of the codes in this embedding. This is a continuous embedding coming out of the encoder. We want to compute the distance between our embedding and every single one of the entries in our codebook. And that's the key idea. Once we've done that, what we're going to do is select the closest code. Let's say D2 was the closest one. So this was the smallest thing. Then what we're going to do is grab, let's call this code 1, code 2, code 3, dot, 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 right? Those are all our codes. Then we'll take a copy. We'll take a copy of code 2. We'll pull it out, right? So we're going to take code 2. Let's put it here. Here is our code 2, right? And again, we selected code 2 because our embedding was closest to code 2 as opposed to all the other codes. And then this code 2 will now go to the decoder to again reproduce our happy face. And so that's the key idea. In the vector quantized variational autoencoder, when we compress our data down, instead of passing the compressed representation to our decoder, we first find the distance between our compressed representation and all the codes that are available to us, and then pass that to the decoder. And this should remind you of K-means actually, right? Like for example, what we're doing is, why are we finding the closest one? For the same reason that every point in this continuous red space, for example, is assigned to its closest centroid, right? Its closest cluster center, and that's this one. So that's why we're using closest. And if you read the paper for the VQVAE, they actually make a lot of analogies to K-means, which is why I'm trying to just mention it. But I'm not going to go into exact derivations there, but that's the key idea. Now, we have a little bit of a problem, and this is our broken derivative. So let's kind of talk about it this way. So what we're going to do, right, what we want to do is go through each part, or so we're going to go through all of the loss bit by bit, but let's just look at the most important part first. What I want to do is take the derivative of our code vector, let's call it E, with respect to our encoder output Z. So again, remember our encoder, I'll just draw it this way, X goes into the encoder and it produces a Z. And then Z goes to our codebook, right? Codebook, which is full of codes, and we find the closest one, and let's call that closest one EI, right? The ith one, right? That's what we selected. And so what we're going to do is just like derivatives, right? Everything in neural networks needs to be backpropable, right? We need to be able to take the backprop the chain rule. So we at some point need to compute the derivative of E with respect to the derivative of Z, right? As we're chain ruling back through these operations. So let's see. So if we do DEI, right? Because we have our ith index, and then DZ, right? If we're doing this derivative, and let's say we're doing it on the Z minus EI squared, right? Because we did define the closest code, we just use the mean squared error distance. You can, again, obviously use any distance metric you want, but we're using mean squared error. So let's say that's what we did. We have our mean squared error distance. Then what we're going to do is our, okay, so, and then the next step. So this is step one. EI is then selected to be the minimum, right? The minimum I, right? Whatever is the smallest distance. And so that's going to be Z minus E squared, right? We're going to pick the smallest one, whatever's closest. And so let's plug this in, right? Let's plug this in. So we're going to plug this into here. And so let's do it. So we're going to do DE, the ith one, is going to be DZ, right? DZ. And we're going to do it between Z minus the minimum I, and then it's going to be between Z minus E squared. There we go, right? So yeah, that'll work. Yeah, that should, a little bit forced notation, but it should be fine. And then we are doing the square of all of this. So let's add the other parenthesis. It doesn't matter, but there we go. So that's what we're doing, right? This is our end goal. We identify the mean squared error, and then we take the mean squared error, right? That's the entire process here. Now, here is the problem with chain rule. As we do our chain rule, so let's do it, right? So chain rule is going to be, this 2 is going to come out in front, so it's going to be 2 times Z minus the minimum of I, and then it's going to be Z minus the code that was selected, right? The internal one, that's going to be squared, times DE, because you have to keep going, right? We have to keep going into the chain rule. So we did the outer one, and now we want to do the derivative of the inner one, which is going to be min I Z minus E squared. And here's the question I want to put forth. What is the derivative of a min function? What does it mean to take the derivative of a min? And if you can't think of any, that's because there isn't one. There is no derivative of minimum. And so we now have a problem. This entire, okay, we want to map to the closest code book, or the closest code to our embedding. but there's no way to differentiate across this operation, right? There's nothing I can do about it. And so the VQVAE paper adds a couple additional losses called the codebook loss and commitment loss to hopefully estimate this. They also have another method using a dictionary learning update method, but we're not going to go into that much detail today. And in practice, this is the loss that's typically used. In a future video, we are going to talk about the Gumbel softmax quantization, which is a differentiable approximation of the min operation. So we're going to kind of leave that for later. But for today, we're going to talk about basically how do we get around this min? What do we do? And so let's kind of do a little bit of a kind of mess around with it a little bit. We'll come back to that a little bit later. Let's just kind of check on the gradients first, and then we'll talk about where the variational autoencoder went. All right, let's go ahead and write a quick quantization module, and this is going to give you an idea of a lot of why backpropagation is breaking. And so all we're going to need is import torch torch.nn, and there's a great package that lets you visualize the computational graph in PyTorch called torch view. So we can do from torch view import draw graph, and I think this will really help us identify exactly what's going on. And so let's write a very simple class quantize, and we're going to do nn.module, right? Very simple method, super.init. And what we're going to do is create a linear layer. So this will kind of act as our encoder, self.encoder. It's going to be a linear layer that takes one input, one output. And then we'll have our codebook. It's going to be nn.parameters, right? nn.parameter. And it's going to just be a tensor, torch.tensor. And this is going to be, this codebook is basically some embedding dim, like how many numbers do we want to use to represent every code. In this case, I have one output in the encoder, so we're going to use one number to represent every single code. And then you can have as many codes as you want, right? That's completely up to you. But for now, we're just going to go with, there's 4 of them to keep it simple. So we can then do torch.tensor, and let's just do -10. The numbers don't really matter. 0, 4, 3, whatever. So now that we have our parameters, we can now do self.decoder, or let's just call it decoder, is again nn.linear 1, 1. Right, so we're going to take a encoder, we're going to take our data, pass it to the encoder, and then we're going to compute its distance from all of these codes, pick out the smallest code, and then pass that code to our decoder. So let's go ahead and do that. So we're going to do def forward self x. And so just like I mentioned, x is going to be self.enc, right? We're going to encode x. And let's do this with some dummy data. So we're going to do q is quantize, our x is torch dot whatever ones, and let's just add a batch dimension, so unsqueeze 0. So there's our data x, and we're going to pass it into q. So we're going to q x, and if we print x out, you'll see this, right? So there we go. That is our, the output of the encoder. And now what we want to do is identify which code is closest to our encoder. And again, there's all sorts of distance metrics you could use to do this. We're just going to use mean squared error. So we're going to do, and actually let's call this z because it's the output of the encoder. So that's our typical notation. So our closest is going to be, let's first do z minus self.codebook, right? And if you print closest, and we're going to square it, right? Because it's a mean squared error. So what we did is took the difference and squared them up, and here we go. And we can clearly see that this is the closest one because it's the smallest distance. And so if we want the index of the code, all we need to do is a quick torch.argmin, and we're good to go, right? So this gives me, every run will be a little different, but that gives me everything we need. Okay. Oh, wait. Argmin needs to go around everything. So let's add one more parenthesis, and there we go, right? So in the one index right there. So 0 is the closest thing, and so there we go. And so now what we're going to do is index the closest thing and pass it to the decoder. So our EJ, let's call it, right? That's what we have is self.decoder, EJ. So this was our closest code. So actually EJ is going to be our, going to be self.codebook closest. There we go. And so we've indexed out, right? Select backwards. We've indexed out our whole code. In this case, it's just one number, but just to keep it simple. And then we're going to pass this code to our decoder. So we're going to do our decoder. Let's call it D is self.decoder EJ. And then we return D. Okay, let's see what we're missing. Oh, okay, we need to add that dimension back. So let's actually do dim equals -1 here. Okay, there we go. Yeah, so we lost a dimension when we did the argument. We just want to make sure that dimension stays, and now we're good to go. So we have now passed it through and we're done. So this is the output of my decoder. So all I've done is take data, pass it into the encoder. I then find the closest code using mean squared error. I find the index of the closest code. I index out the closest code, and then I pass that to my decoder, which is exactly what I described here, right? We grab our embedding. We then compute the distance between this embedding and all of our codes. We then find the closest one, select it, index it out, and then pass it to the decoder to do our deconstruction task, or decoding task. And we're basically done, except for one problem. Let's call this out is QX, and we can do out dot backward. All right, this is going to go ahead and compute our gradients. And when we do this, and I'm just going to copy this little part here, this is to actually visualize the graph. You'll see something like this. So we have a gradient flow, right? This is basically the chain of operations that happen. We had some tensor, it went through a linear layer. We did some subtraction, right? That was this right here. We then squared it, right? That's our power. We did an argmin, we did a get item, right? That's the indexing. We did a linear layer and then an output tensor. And that's basically our entire setup, right? That's all the operations we did. Except notice that this backpropagation path goes through argmin, and there is no gradients. There's no way to compute a derivative on an argmin, and we can actually verify that, because if we take a look at the derivatives, if we do if you look at the encoder.weight.grad, it's going to be none. So it didn't actually even print anything out because there is no gradients. If we print it out, then it'll actually print none. It couldn't do it. And so we have a problem. Basically, and let's draw a kind of cleaner version of this. You have your encoder, and then you have your decoder, and you have this codebook up here, right? Let's call it codebook. And your data goes into the encoder, it comes out of the encoder, and then goes to the codebook, where we select a code that comes out and then goes to the decoder, right? And unfortunately, this entire operation here, this whole operation has no derivative, right? Because we have to use that min operation to do any of this. And so we need to do two different things. The first one is we need to copy gradients from the decoder to the encoder, because it's important that gradients, right? Let's use red. It's important that gradients flow through the whole model. We'll deal with the codebook a little bit later. For now, what we need to do is make sure that gradients that are backpropagated through the decoder are copied over, basically circumventing this entire operation, just copied over to the decoder so we can keep going, right? That's step one. So let's go ahead and see how we can do that. And there's actually a couple ways you can do this. You can write a custom backward model module. There's actually a bunch of ways you can do it. But we can actually do this very simply using this trick, which you might have actually seen before. But this seems like you're not doing anything. You have, so let's make this clear. So we have, let's say we have, let's use this color. So we have the output of the encoder, Z, and we have the output of the decoder, right? Or the input to the decoder, EJ, right? That's what we have. And what we need to do is make sure that we can copy gradients from here to here, but we never want to do DEJ, DZ, right? We want to never have to do this derivative, but we still need to move that gradient information across. So what we can do is we can say that EJ, so this is after, right? So we're going to do our forward pass. We're going to say EJ is equal to Z plus EJ minus Z dot detach. And let's kind of pick this apart piece by piece. If this detach wasn't there, right? Let's say it wasn't there. Then all we would have written is EJ is equal to Z plus EJ minus Z, which means that all we have really is EJ equals EJ. So it feels like we didn't do anything, but we actually did something important. And this is just a trick for how PyTorch's AutoGrad works, right? So all we're doing here is a trick for PyTorch AutoGrad, but this trick allows us to do one other thing. So all we've technically written is EJ equals EJ. So we didn't change the value when we did this operation. So that's good because the value didn't change because we want EJ to be that code that we got from earlier. On the other hand, when we do EJ equals Z, when we do d EJ dz, this derivative, this is just equal to 1. Because if you remember in PyTorch, detach is to remove, right? Remove from graph, right? So this whole thing here, as far as AutoGrad is concerned, this is a constant, just some C. It's just some constant, and this constant exists just to make sure that EJ equals EJ. So all PyTorch is seeing is EJ is equal to Z. None of that extra min operation, all that stuff. It's just EJ equals Z. That's all it sees, which means the derivative of one thing with respect to the other thing is just 1, right? And so this is how we're going to copy gradients, because we're again going to have, in the end, right, we're going to have some weight here. Let's say call this weight 1. We'll have some weight here. This is going to be some weight 2. Right, and we're gonna backprop. We're gonna have some loss at the end, so we need to compute dl dw2. Right, that's a derivative we'll have to do, and then we'll do dw2 dej. So we'll then have dw2 dej. But with all the min operations we did, to get to w1, we have to go through z. Right, that's where it came from. So we would have to do dej dz. And then dz dw1, right? This is what we would have to do. It's just this whole operation right here was not possible to differentiate over, which means this derivative did not exist earlier. But if we just add this extra little bit of code, which looks like EJ equals EJ, but really this whole thing's just a constant, and this is just saying that the derivative of EJ with respect to Z is just 1, then this whole thing is 1, and that's how we're going to copy derivatives over, right? Because we didn't change anything. We can then just directly do chain roll, and PyTorch is none the wiser, right? And that's the key idea. So let's go ahead and implement it. I think it's easy to see if you just look at the visual. So what we're going to do is just copy what we had from earlier, right? Nothing has changed. But we're going to add one more line. So we're going to first do, let's do that. Let's comment U out. So we have the same setup, same everything. But now, after we index, EJ is the closest code that we have. What we're going to do is we're going to say EJ is equal to Z plus, so EJ equals Z basically sets everything up. But if we set EJ to Z, then we don't have the code anymore, right? So we have to remove the Z essentially. So we can do EJ minus Z dot detach. And that effectively is saying EJ equals EJ, but PyTorch treats all of this as a constant. So when it does the backpropagation, it'll use this, but the value it'll use is EJ. And that's the key idea. And nothing else changes. This now gives us actually something interesting. So notice we still have this subtraction, power, argmin, get item, whatever. So we still have to go through this path, but this path here has no derivative because of the argmin. On the other hand, this path, see how additional paths have shown up? This path going from the add all the way back to the linear, and that add is basically this add right here, this add going back to linear. We now have a pathway for those gradients to flow. And this is exactly the trick for VQVAEs. If you take away anything from this video, it's understanding this little chunk of code, because you see it actually quite a bit in lots of applications, especially those for these quantization methods. So there we go. That's how we can copy gradients. Again, we could have written a custom PyTorch like backwards method that does this as well, but this is just shorthand, right? We're going for simple here. So okay, good. So I'm going to copy stuff. So again, a lot of this code is going to be very, very close to the stuff that we've done already. So I'm not going to bother going through all the nitty-gritty details. Again, we just take a look at my AutoEncoder video for that. Instead, what we're going to do is just explore the VQVAE. Now, before we do that, I hope you now understand the purpose of quantization, right? Quantization is basically we have k discrete codes that we can map our continuous distribution to. And the larger the k, the more mappings that you can learn, right? So the more that your k is, the more representations you can have, right? And k is basically a hyperparameter choice, just like in k-means clustering, right? K, how many cluster centers you have, is a hyperparameter choice. But there's still a couple things we haven't talked about. Number one, we have the derivative to update our, right here. So we have the derivative to update our model. So we're copying gradients from the decoder to the encoder, but this codebook has no gradient. There's no derivatives here. There's no information there for it to update because the codebook has to be trained just like everything else. So how do we get gradient information there? So that's one question that we still need to answer. And the second question is, this is called a vector quantized variational autoencoder. Where is the variational autoencoder, right? Like we're not mapping to a Gaussian, we're not doing, where's the variational autoencoder, right? Because the entire purpose of variational inference is to map to a known distribution from some high dimensional complex distribution. That was the entire point of the VAE implementation we talked about last time. So let's go ahead and answer the second question first, and then we'll talk about how we update the codebook either. So the question is, where's the VAE? Let's kind of think a little bit about what we did. We have some Q, and let's use a different color that's not red. Let's do, we have some Q, and we're gonna have some Z equals K, some code, given X, right? Before, in our VAE, right? In our VAE, we said Q, Z given X, right? We want to map to some Z given X, and we wanted that to be Gaussian, right? We want it to be Gaussian. But now it's not just Z given X, it's Z equals some specific K, some specific code given X. And this is going to be, if we look at the distribution of it, right? This is actually just 1 if K is the closest, if K closest, and it's 0 otherwise. Otherwise, right? So if K is the closest code, then it's 1. Like 100%, this is the code. And if it's not, then it's not. And so technically, what we can say is, if we have our codes, right? If we have all of these codes, and we have code 1, code 2, code 3, ... code K, and each of them are embedding to me, but that part doesn't really matter. It is a fair assumption for me to assume that the distribution we want is uniform. And the reason I can say that, so with probability 1 over K, and that's because each one of these codes are equally likely. There's no reason that the model would, if you like every code is equally likely to be selected, right? Every code is equally likely. On the other hand, like a Gaussian, right? You're more likely to pick the stuff in the middle than the stuff on the edges. But in this code book, there's no reason that I would pick one code over another. So an assumption we can make is, why not make it a uniform distribution? And this is exactly what the VQVAE paper does. They go ahead and do the uniform distribution, use a uniform distribution to kind of call it a variational encoder. So now we're mapping from our high dimensional data to a uniform distribution, specifically a discrete uniform distribution with K codes, right? So discrete uniform distribution. So let's remind ourselves a little bit. What was our KL, what was our ELBO loss, right? In VAE, we wanted to solve the ELBO loss. So again, I'm going to just assume you know this because you saw that video, but it's going to be DKL plus our reconstruction, right? Reconstruction is exactly the same. It's going to be the mean squared error loss. That's going to show up again. So let's just look at DKL for now. So DKL, if you remember, what was the formula for it? And let's kind of be a little bit more specific in the notation. It's the KL divergence between our Q, right, which is our predicted distribution parameterized by theta. This is going to be Z given X, or Z equals K given X. And we want to find its distance with P of Z, right? PZ. There we go. So we want to make sure that, we want to minimize this distribution as we're learning. And this specifically, if you remember the formula for the KL divergence, it looks like this. It's going to be Q theta Z given X, and then with P, or sorry. It's going to be log. And then, right, it's just a standard KL divergence formula. So it's going to be, again, Z given X and our P Z, just like that. And the sum is over, and it's a sum because it's over the discrete space, right? Z equals K. And so this is our simple KL divergence formula, right? Just like before. But let's now start to plug in the stuff that we have. Number one, our Q theta Z given X, right? Our QZ, right? This here is going to be 1 if it's the closest one and 0 elsewhere, right? That's all it can be. We give 100% probability to the closest code and 0 everywhere else. It's not like you can have a part of one code and a part of another one. No, it's 100% probability to the code that we get, 0 everywhere else. So if we're doing the sum over Z equals K, this value here is only 1 for the closest code vector, right? It's only 1 for the closest code vector, and it'll be 0 everywhere else. So now we can get rid of the sum. We can just say this is equal to Q Z equals, let's say, K hat, which is the closest code vector given X. There we go. And again, we're going to have the same log, and this will be the same again, Q Z equals K hat, our closest code vector given X, divided by PZ, right? And now what is my assumption? I assumed that PZ is uniform over my K possible codes. And this whole expression is just 1 because it's 100% this or 0% anything else. And that's why it's 1. So we can rewrite this as 1 times log 1 over K. And this is equal to log K. And K is a constant, right? K is a constant of how many codes we have, which means log K is a constant, which means in our loss function, it doesn't care, right? Whether or not I have a constant, so now I have basically my final loss function is I want to minimize negative DK, or my ELBO loss, right? So we have negative DKL plus reconstruction. Whether or not I'm even including this, if this is just some constant C, then it doesn't matter if it's included or not included, and I can just keep the reconstruction loss. And so this is why it is it's still a variational autoencoder. It's just the variational part disappears. It disappears because we're mapping to a uniform distribution. And as we can see, the KL divergence, the thing we wanted to minimize, just ends up being a constant. And if it's a constant, then it really doesn't need to be included in our loss function. You could include it, it just wouldn't change anything, right? Because minimizing something and minimizing something plus a constant is the same minimum. It doesn't change anything. So, okay, good. So that's number one. The next question, how do we pass gradients to our codebook, right? So this is the other hurdle that we have to make, and this is actually the novelty of the VQVAE paper, right? And they do it through the codebook loss and the commitment loss. And there's a bunch of interpretations for this, but here's basically the main idea. So we have, again, we encode data, we produce some code, this code goes to some code, or we produce some Z, goes to some codebook. The codebook will find the minimum thing, will produce some, let's call it EJ, right, the closest one, and then this goes to the decoder. And with that, with the gradient trick that we just saw earlier, I can copy backprop gradients from here. It's going to just kind of skip over this whole operation and then just keep it going. But if we skip it, we need to compute gradients here. Otherwise, how can we update our codebook? These are learnable parameters, just like everything else. So to learnable parameters, we need to do a little bit of work here. And the way they set it up is they use something called the codebook loss and the commitment loss. And they do it with stop gradients. So first of all, what we need to avoid is any opportunity to do DEJ, DZ. This is not allowed because this is a a non-differentiable operation. So we have to find another way around it. And so the first one they do is the codebook loss. So it's called a CB loss. And this is basically the norm. They use a stop gradient operator. The stop gradient is just the detach that we did already. It basically means that everything inside the stop gradient operator, so if we do Z, E, X, whatever, right? So I'm just trying to keep it to the notation. Anything that's in here, basically the Z, right? All we care about. Let's keep it the same as mine, so it's very clear. Stop gradient Z. Anything inside here, we take off the computational graph. So this is treated, anything inside the stop gradient is treated like a constant by PyTorch. And we're going to subtract E from this, and we can do a 2 norm, whatever. And so this codebook loss will update. So all we're doing is we're trying to minimize the distance between our codes E, right? Our codes E. Let's keep this clear. We want to minimize the distance between our codes E and move them closer to our output Z. So the big idea here is the codebook loss will update our code vectors in the codebook by moving them closer to the output of the encoder, right? So we're trying to move CB in the direction of Z, our code's in the direction of Z. But we are doing this by treating Z as a constant, and as long as it's a constant, we don't have to do the DE/DZ operation. So that's great. So this is now going to move our codes towards the Z, and it acts like a approximation for a gradient, right? For some type of derivative. On the other hand, we also have the commitment loss, which we'll call commit loss. And this is exactly the opposite. It's going to be Z minus stop gradient E. And the commitment loss is basically the opposite of the codebook loss. It ensures that the output of the encoder is close to our code vector. And when it comes to the commitment loss, we allow for a beta parameter here, or there's going to be basically a beta constant that goes in the front that allows for a little bit of divergence. But the main idea is that we're basically approximating what the derivatives should be inside here, inside our codes, by trying to move the code vectors closer and closer to the output of the encoder while treating it as a constant. And I also want the encoder to push its outputs closer and closer to the codebook, again, while treating it as a constant, right? So in both of these operations, there is no DE/DZ operation at all. And this is the key idea of the VQVAE, and this is basically the novelty of the entire paper. And so now that we kind of have all the pieces, I did a lot of talking here, but I think it's just really cool, so I wanted to talk about it because we're going to be using this a ton for harder future implementations. But let's go ahead and write a standard vector quantizer. There's actually a couple ways you can do this. There's an indexing method, there's a scattering method. I'm going to do the dumb method because I think it's the easiest to understand. I don't think there's all that much difference in efficiency, but quantizer, nn.module, definite. And this is basically needs a couple things. So first, codebook size. Let's just do a small one for, actually, let's just keep it this for now. And latent dim equals 2. So again, for the purposes of visualization, I want to compress my data down to just 2 numbers. So I'm going to have my codebook be 2 numbers, but I have 1024 distinct codes that I can map to. And this is the key idea. The encoder can map to any discrete or any continuous number it wants, right? It can be any, it's basically if we're outputting 2 numbers, it's on the R2 real space, right? It's on the entire coordinate plane. But by restricting myself to just 1024 different points, we're basically limiting the types of embeddings that our model can have. So that's why it's quantization. It's basically like rounding, right? We're taking some large continuous space and representing it by some limited set of discrete space, right? Some limited set of discrete tokens or codes. So let's go ahead and implement this super.init. And what I want to do first is just set it up. So we did parameter before. You can still do parameter, but we're going to use an embedding matrix. It doesn't matter. Embedding is equal to nn.embedding. We're just doing this because it'll initialize it to begin with, but codebook size by latent dim, right? That's our setup. And we will also go ahead and just do self.embedding.weight.data. We'll just do the standard initialization, which is going to be from -1 over codebook size to 1 over codebook size. So for what we're doing today, this MNIST is so easy that this actually won't care. So there we go. We're going to store some of this information. Latent dim is our latent dim, and self.codebook size is codebook size. And so we're going to implement this in two different ways. We're going to do def forward self x. We're going to do efficient equals false for now. For now, we're going to do the inefficient way, and then we'll just do the efficient way afterwards. And hopefully this will all make sense. So step one, what we're going to do is store our batch size is going to be batch size, it's going to be x.shape 0, just like that. And let's go ahead and create some random data here for us. So I'm just gonna copy u in. I just create some random data out of the codebook. Let's do a codebook of size 8, and let's do a latent dim of 2, right? To keep this simple. That means this is gonna be 2. And we're going to pass in 4 samples, each with 2 things. And rand, remember rand, rand can be anything. It's some continuous thing. We're going to map our continuous output to one of these codes. So let's go ahead and do that. VQ rand. We have our batch size, that's 4, that's fine. And so the first step is we're going to do if not efficient, which is what we're doing right now. We're going to do the very simple pairwise distance calculation, right? So if you remember, right, let's kind of recap exactly what's going on. We have a data of batch by 2 right now, right? So it's 4 by 2. And so we have 2 numbers representing every one of these samples. And we have a codebook matrix, right? We have a codebook matrix that looks like this. It's going to be, it's going to look kind of like this, right? Lots of codes. We'll have the number of codes by our 2, right? Because we're using, again, 2 numbers in the codes. And what we want to do is compute the pairwise distance. That means I want the distance between this and the first code, this and the second code, this and the third code, ... And then I want to repeat that for the second one, right? I want to compute the distance between the second sample in the batch and the first code, second sample in the batch and the second code, second sample in the batch and the third code, ... Oop. Right? So we're basically computing the distance between every combination of my samples and all of the code. So we get every pairwise distance. And we could have actually used cdist. There's a function built right into PyTorch that does this, but I want to do a little bit of this on our own. Otherwise, this would only be 2 lines. Okay, so let's go ahead and do this. We're going to do embedding. It's going to be, so let's kind of get the shapes right. So we're going to be we have our embedding, which is currently a C by L, right? This is our embedding matrix. And our data, right? Data is going to be batch by, let's see here, batch by, and let's do L. Or is it L? No, let's do batch by E. Or let's see, we have number of codes by also E. So let's just keep it the same. Okay, so we have in our embedding matrix, it's number of codes by the latent. I guess that's why I called it L. So let's just try to keep it the same. There we go. Right, so it's our number of codes by our latent dimension. And then the data is batch by that same latent dimension because we ensure that they're the same. And so what we need to do is compute every single pairwise distance between every single thing in the batch and everything along C. And there's actually a few ways you can do this, but let's just do it the dumb way first. We need to add a batch dimension to embedding because we need to repeat this operation, right? We need to repeat this pairwise distance for all samples in the batch. So what we're going to do is embedding is self.embedding. We're going to grab the weight. I guess we could have used a nn.parameter as well. It would have made no difference because we're accessing the weight inside the embedding anyway, but it's fine. It doesn't matter. Unsqueeze 0. And then we're going to do dot repeat batch size, and then we're going to leave the other dimensions alone. So if we print embed.shape, we are now at an efficient. Oh, there we go. Okay, so we have repeated our code book, right? Our code book of code by latent dim 8x2. We've repeated it 4 times, once for every single sample. And now that we have that, we need to do one more thing. We have now a batch by embedding dim by C. And what we need to try is to compute the distance between every single thing in this batch and every single thing here. But we're missing a dimension, so we can actually add a 1 here in the middle. And that'll let it work. So if we now do it, so let's take our data, x is equal to x.unsqueeze 1. We want to add in the middle, so print embed.shape, x.shape. This sets it up such that we have a batch size in both of them. We then have a number of codes by embedding dim here, and then our just dummy dimension by embedding dim here. And I want to compute the mean squared error distance between this and all of these. So between our 1 code that we have per thing here, or 1 output, our z, and all of these things here. And so this just works out very simple. We just do distances is equal to, we can do x minus embed squared, right? That's our setup. And we want to do it along the last dimension. So again, let's just try to be extra clear here about how things are working out. We had a, let's do smaller examples. We had a batch by 2. We then had a number of codes by 2. And what I want is just to repeat this operation for everything in the batch. So what we did is we took our codes by 2 and turned it into something like this. We had codes by 2, but we've repeated it batch number of times, right? There we go, right? Batch number of times. So repeated batch number of times. So now we just have a bunch of copies of this code book over and over again. And then I took this batch dimension and I added an extra dimension. So now it became, we have, if we take this here, we have batch number of our 1 by 2. So we have a 1 by 2, 1 by 2, 1 by 2, dot, dot, dot. And we have a batch number of them, right? Because in this case, we had 4 of them. So we basically took this first thing and put it here. And then we took this second thing and put it here. That's basically all our dimensions are doing. And then we're taking the mean squared error between this pair. And then we're taking the mean squared error between this pair. And then we're taking the mean squared error between this pair. And PyTorch, when you take the mean squared error, will automatically broadcast this tensor along this entire dimension. And it'll broadcast this tensor along this entire dimension. And that's the key idea. So that's all the operation's doing, just to try to be a little bit more clear about these more annoying tensor manipulations. And so then, now that we have this, we have our print distances, right? So we end up with these distance. We end up with 4 different distance matrix of. This is how the first sample was. This is the distance from the first sample to the first code. Second sample to the first sample to the second code. First sample to the third code. Dot dot dot. And then again, the second sample to the first code. The second sample to the second code. The second sample to the third code. Dot dot dot. Right? And we repeat that for all of them. And so once we have that, we just need to add them together, right? We just need to sum them together. And so we can just do torch.sum. And that'll give us our final distance, right? This is standard distance formula. Dim equals -1. And so we end up with this, right? This is my square distance, whatever. And I should technically take a square root, but the minimum of something and the minimum of the square root of something is the same thing. So it doesn't really make a difference if we add that square root or not. Then it'd be like Pythagoras theorem, but it's fine. So we have our setup here for our computation. And this is all we would need to do, and we'd basically be done. So we could just keep going. But I'm going to do the efficient version. And the problem with what we just did here is this line right here. We took our embedding matrix and repeated it batch size number of times. So what we've really done is we've inflated our embedding matrix. And you can imagine if you have large embedding matrices in your model, and you have to and you're doing large batch sizes, like a batch size of 1,000, then that embedding matrix is going to get copied 1,000 times and eat up a ton of GPU memory. So you want to avoid doing that, and that's why we're going to do a slightly more efficient version. So we're going to do else, or you could have just used, again, cdist from PyTorch, but that's fine. So let's set our efficient to true now, else. And so now we can do L2. So, okay, so let's set it up. So our target thing that we want to do is L minus C squared, right? L minus C squared. But don't we have a formula for that? That's just L squared minus 2LC plus C squared, right? Let's write C2 for now. So we have a formula for this, so why don't we just do it that way? So let's do L squared first, and then the other ones will kind of just make sense. So let's do L squared. This is going to be so our data, again, if you remember, is batch by L, right? Batch by L. And so what we want to do is just square it up and add it together, right? That's the first operation. We're going to square it up and then add it together. So let's do that. So we're going to do x squared, right? That's the thing we want to square on, x squared. But we need to now add it up just for the same reason we did the sum here, right? We want to add it up because in the end, we're going to sum all of these things together anyway. So we've squared it, and now we can do torch.sum dim. We want to do it along the last dimension, and we're going to do keep dim equals true just so it doesn't lose that dimension. So now we can print L2, and this is my x squared, right? So we started with print x. So this is my data, and what we want to do is x squared, and then in the end we have a sum, so we're just doing the sum right now. So we do x squared and then add them together, and that gives me this. And this is basically a partial of my L minus C whole squared, right? We're just doing this entire operation here. It's the same operation, we're just doing it in pieces rather than all at once, and that's the key idea. So we have our L2, no problem there. What about our C2? It's going to be exactly the same thing. We're going to do our C2. It's going to be, and this is going to be our self.embedding.weight. These are our embeddings, right? Our codebooks, weight. And we're going to square our codebook, right? We're going to square our codebook. And then again, we're going to do torch.sum. Dim equals, we can do it along the last dimension. And then again, keep dim equals true. And there we go, right? That sets this up. And now that we have this, so we have C2, we have L2, and we just need to now put it all together with the minus 2LC. Is this dim equals minus 1 or? Okay, yeah, no, we're good. Yeah, it's the same thing anyway. So there we go. Now we have to do the 2LC. So how do we do that? We can do first, let's call this LC, is going to be X, and it's just a matrix multiplication, right? It's just a matrix multiplication between our embedding dimension, or our data X, and self.embedding.weight. And we're going to have to go ahead and transpose it, right? We have to transpose it to make it to work, because if we can check print x.shape, self.embedding.weight.shape, you'll see that our x is batch size by embedding dim, and our codes are code by embedding dim. But we want to find every pairwise relationship, right? So we need to then, we want every one of these with every one of these, so we have to transpose it. And so we end up with print lc.shape. And you'll end up with this, right? 4x8. So this is the matrix multiplication of how everything is related with every other thing in the code, right? The partial of that distance computation. And so this is, again, very simple. Just our regular, we're just taking this and chunking it up into a couple pieces. Now that we've done that, our distances is going to be, distances is just going to be our L2 minus 2 times LC plus C2. Okay, looks like there's a bug here. So we have batch by channels. Let's double check here. Print lc.shape. We have 4x8. Let's print all of them out. Print l2.shape and print c2.shape. Right? Those are all of our shapes. So we have batch. Oh, it looks like this is not a batch dimension. So we need to do, oh, yes, of course. Because this is the distance over our C2. So if we print out C2, we just have 8 numbers of the C squared values, right? 8 numbers. But this one we can now repeat for the batch dimension. We still have to do this repetition for the batch dimension on our codes, just like we did before, except instead of expanding out some giant embedding matrix, I only need to expand out my summed squared values, just like we have here. So we can actually just add that right here. We can do dot unsqueeze 0, adding in the batch dimension, and then PyTorch will automatically broadcast over it. So this is what we have now. So our LC is the relationship, the relationship between L and C, and basically is our distance, a partial distance computation. And it's our batch size, everything in the batch, by our codes. And then we have our computation of x squared, or L2 squared, or L squared, basically. That's just our batch size. And then we have the computation of our C squared. That's 8, and we just kind of include this dummy dimension for the batch size. And then PyTorch can just add these up and then go ahead and do the operation. And that's basically it. That is our distance calculation. So I would recommend doing this once on your own. If you kind of follow the tensor in a, kind of like, line by line a little bit better, then you'll see that this operation and this operation are doing exactly the same thing. All we've done is take this, this thing here, L minus C whole squared, and just chunked it up into our typical A minus B whole squared formula, allowing us to do every piece one at a time, and allows us to avoid doing this massive like inflation on the batch dimension. Notice there's no repeating here anymore, because PyTorch will automatically do the broadcasting for us. So that's great. So this now gives us our distances. So our closest, right, they'll both give the same thing, but our closest is going to be torch.argmin distances dim equals -1. So along each row, so print distances, if you take a look, this is how everything, this is how the first sample was, how close it was to the first code. How the first sample, how close it is to the second code, to the third code, the fourth code, fifth code, ... Again, how close is the second sample to the first code, second sample to the second code, ... And so we get all of these distances. And what we want is, what is the closest code? So we want to find the argmin, right? The index of the closest code along each one of these things. And so we can do here, print closest. Right, so these are the codes that are selected. Of course, every time we run it, it's going to be random, right? So there you go. So these are the indexes that have been selected as the closest code. And so what we're going to do now is we need to grab these specific codes from our codebook. And there's a bunch of ways you can actually do this. Let's do it with our kind of dumb way for today, just so I don't want to get into scatter and gather right now, because that'll push us off a little bit. We'll talk about that later, so it's fine. So we're going to do quantized latence index. It's going to be just, let's call it torch.zeros. We're going to create a thing of zeros of shape batch size by self.codebook size. We're just going to create this thing, and we're going to make sure it's on the right device. Device is equal to x.device. So all we've done is created a quantized latence index, and we just create a tensor like this. And what we're going to do is fill in for the indexes that were selected, right? So here are 8 possible codes. One of those 8 have been selected as the closest one. So whichever one's closest, I want to fill that in with 1, right? So we can do that. We can do, we can create a fake batch index. So batch index is torch.arange batch size. So our batch index is just going to go from 0 to 3 in this case. There we go, right? 0 to 3. And what we're going to do is in our quantized latence index, indexed at the batch dimension, so batch index, and at the closest, right, whatever was identified as closest, we're going to set these to 1. And so then if we take a look at this, you should see that we get a 1. And let's also print out the closest so we can compare. Closest. There we go. So we selected index 3, or code 3, code 3, code 0, code 6. So let's see, 0, 1, 2, 3. So code 3, 4, 5, and then 0. So code 0, and then code 6. So all we've done is created a matrix of zeros and ones that have selected all those codes out. And now all we need to do is a very simple matrix multiplication. We can do our quantized latents. Latents is going to be quantized latents index at self.embedding.weight. And the reason this is going to work, if we look at print self.embedding.weight and print quantized latents index, the reason this will work, I keep spelling this wrong, should use a shorter name, is that our embedding weight is 8 by 2. And our latents, our latent index, is 4 by 8. So we're multiplying a 4 by 8 matrix by a 8 by 2 matrix. And so let's work out the matrix multiplication. So what we're going to do is multiply this row by this column. And notice how we want the second code here. So, or basically the third code. So code 1, code 2, code 3. So the third code was selected in this in this operation. When we did the min, that's our closest. And so by doing a matrix multiplication, every other code, let's just take this first row for example, every other code will be zeroed out because we're going to multiply by zeros, except for the code that we want. So it's going to be, for the first column, it's going to be 0 times this, which is 0, and then 0 times this, which is 0. But then we're going to have a 1 times this, which is going to say that we want this code, right? That's what we want. And then it's going to be 0 times everything else. And then similarly, when we do the next column, it's going to be 0 times the first two things. It's going to be 1 times the thing we care about, and then 0 through everything else. And it's going to add it all together. And when you add it together, you'll get 0 plus 0.0875, and you get a 0 plus 0.1093. So nothing changed. We just did a simple matrix multiplication to index these things. Again, we could have used the scatter operation, which is even better, but I don't want to go into too many rabbit holes for this. And so there we go. And if we print out our closest, let's make sure, and print out our, let's see here, our embedding weights, then we can verify that what we expect happened. So the first code should be the first sample selected the fifth code. So let's see, 0, 1, 2, 3, 4, 5. So we selected this code. Is that the code we picked? Minus 0.0365? Yeah, of course, that's the code we picked. The second code picked the fourth one. And we actually picked the fourth one twice, and we can see that happen. 0.0722, we repeated that twice. Then we have the first code, which is going to be 0.04, 0.04. So this is how we are doing this entire operation. And that's it. We're going to now return our quantized latents. And we are done, right? This module here is basically half the novelty of our vector quantized variational encoder. Now, kind of going forward, I'm going to go a little bit faster because the hard part is done. We're going to spend a little bit of time on the loss function, so I want to make sure we get there. So for now, let's write a simple model: classic linear vector quantized VAE, right? And n.module. Just like always, and we'll have some latent dim equals 2. We'll have some codebook size equals 512. Oh, type that. Let's just use 512. And again, the codebook size is up to you. So in kind of state-of-the-art models, they'll use a codebook size somewhere upwards of 16,000. There are other methods, and actually there's actually some problems with using large codebooks that we're not really going to talk about today. So maybe I'll discuss a little bit about it in the end, but for now, let's just keep going. So we're going to do super.init. And so our encoder, actually I can copy, this is literally the same model as before. So I'm going to copy stuff that we have already. So we have our encoder, bunch of linear layers. Again, we're doing it on MNIST, right? So a bunch of linear layers. We have our codebook, which we've created here, and we have our decoder. And it's as simple as that. So nothing new changed, except we've added this new codebook. In the VQVAE, right, in our vector quantized, in the variational encoder, standard variational encoder, we had two projection, right, two linear layers in here to map to our mean and standard deviation. We don't have any of that now. So we're going to do def forward self x, And just like I had before, we're going to do a def forward encode self x, and then we'll throw a pass in here, and then def forward decode self x. Right? We're going to write our encoding function, decoding function, just like how we did it before. Encoder is very simple. We're going to do x is equal to self.encode x. And we're just going to return x. Nothing crazy there. Now in the, and we're also going to have another one, def quantize self. And we're going to call these z. And let's technically call this z so it's clear, right? Because the output of the encoder, we typically call it z. So there we go. The quantizer, right, is going to take in z. So let's go ahead and do it. So first, our codes is going to be self.VQZ, right? We're passing our codes, right? Or we're passing our embeddings that came out of the encoder into this quantizer that we just wrote, right? So we can produce our quantized latents. So let's go ahead and do that. That's this, right? So our codes are our Qs, our quantized latents. And then we need to do two things. Number one, we need to compute our codebook loss. So let's remind ourselves again. The codebook loss is how we are going to actually update our codebook. So our codebook loss is a stop gradient. We want to make sure when we're moving our output of the encoder closer and closer to the codes, and vice versa, right, for the codebook and commitment loss, we don't actually compute any derivatives between these operations. So we're going to do stop gradient on one, stop gradient on the other. And that's the key idea. So let's do the first one. This is going to be the stop gradient on z, and then we're going to subtract e from, or vice versa. Right? It's square anyway. So we can do codebook loss is going to be, we're going to average it up across the batch, right? And we're going to do codes. So the codes is differentiable still, right? Codes is just normal codes, but we're going to subtract from it z.detach. This makes z a constant. As far as AutoGrad's concerned, it's a constant, and then we square it. And so all I'm doing is this loss is going to try to move these codes closer and closer to z. So that's our codebook loss. We'll move it closer and closer to z, but without actually, while treating z like a constant, right? So z is like a target that the codes are trying to get to. It's basically being treated like a constant. Similarly, commitment loss is going to be torch.mean, and it's just going to be the other way around. It's going to be it's going to be codes.detach. So now we're treating the codes as a constant, and we're doing minus z squared. So now we want the output of the encoder, which produced z to begin with. We want the encoder to move its outputs closer and closer to the codes. And that's basically it. That is our codebook / commitment loss. But this still isn't the full problem, right? So what I've done is I've used z and I've used the encoder, like the encoder, to be able to update our codebook. But we still haven't dealt with the decoder. We still need gradients from the decoder to be copied around this entire operation, right? Just like we discussed up here when we were looking at those derivatives, right? We want the derivative to be a 1. So let's go ahead and do that. That's the very simple. We had our, this is also known as a straight through estimator. So we're going to say codes is equal to z, but obviously codes is not equal to z. So codes is equal to z plus codes minus z dot detach, right? So again, this looks like it's just codes is equal to codes, but this is being treated like a constant, and dz decodes, right? Or decodes dz is now 1, right? So the derivative here is 1. So all we're doing is really copying gradients over from the decoder to the encoder this way. So very simple. And we're going to go ahead and return our codes, our codebook loss, and our commitment loss. There we go. And then our decoder is going to be exactly the same thing, right? For decoder, it's going to be, we're going to pass in a, let's see. Yeah, I guess we can just stick this in a decoder. So in our decoder, we're going to use our quantized functions. We're going to say codes, codebook loss, commitment loss is going to be self.quantize x. We're going to take it, go ahead, quantizer x. And then our decoded is just going to be self.decoder. We're going to pass into our decoder our codes. And once we've done that, we can go ahead and return our codes decoded our codebook loss, and our commitment loss, just like that. And so our final forward pass should be pretty straightforward. We're going to do batch by channels by height by width is equal to x.shape. Right, so there we go. And we're going to do x is equal to x.flatten 1, right? So remember, our images are in the batch by channels by height by width. We just want to flatten it to vectors because we're dealing with emness, right? So there we go. That's going to convert them to feature vectors. And then we can do latents is equal to self.forward. Actually, let's not do latents. Let's do z is equal to self.forward encode function. We're going to pass x to that, our data. And then we're going to get our quantized latents, our decoded output, our codebook loss, and our commitment loss. And this is going to be self.forward decoded. And we're just passing in our z, right? We're just passing in our z and producing all of that. And lastly, we just want to make sure our decoded is back in this shape. So we can just say decoded is equal to decoded dot reshape batch by channels by height by width. That just puts it back in the image shape, right? So we can compute the reconstruction loss very easily. And so we can go ahead and return our latents, our quantized latents, our decoded, our codebook loss, and our commitment loss. Commitment loss. Looks like I'm missing maybe a comma. There. Good, so that's it. So we have an encoder, we have our quantization, we have our decoder, and this is it, right? These are our loss functions to update the codebook, right? And this is the loss, or not loss function, but this is the straight through estimator, allowing us to just directly pass our gradients from our decoder straight through the encoder, kind of going around all of this non-differentiable stuff, right? Because nothing we did in here is differentiable, especially the argmin, right? So we're good to go there. All right, now that we have that, let's go ahead and write a, do I actually want to write a training? I guess I can, I don't really want to write a training loop because, again, this code is basically identical to everything we have done so far. And so I'm just assuming that you've done prerequisites. I'm going to walk through the code instead of talking about it. There's nothing fancy in here. It looks fancy because I have all this extra stuff for visualization and whatnot. Don't worry about that. I'll just point out the key parts. We have our data loader, right? So here's our data. We have our optimizer. We then have a progress bar. And all we really care about is this. So we don't care about you. Because we're only training the VQVAE right now. So the VQVAE will return our encoded, quantized encoded, the decoded, the codebook loss, and the commitment loss. And the reconstruction loss is just the mean squared error between, and we don't really care about the data variance, so let's simplify this more. It's just the mean squared error between our images, right, the true images, and the decoded images. So there we go. And our final loss is going to be the reconstruction loss plus our codebook loss plus our commitment loss. But notice that we have a 0.25 here. This is just a constant that they used in the paper, and it allowed for a little bit like more stability and some more like range of stuff that the encoder can actually represent. So we use a typical beta, like I mentioned, there's a beta parameter in front of the commitment loss. It's typically set to 0.25, so there you go. That's our loss. And then we go ahead and train our model. Nothing else changed. This is fine. None of this matters. There's nothing in here. All of this is for visualization, so I wouldn't worry too much about it. The key idea is this, right? This is our loss function that we're trying to minimize. And rather than actually train it, I'll just show you the results because this is really not that. No one wants to watch a training loop, but here we go. Oh, spazzing out. There. So what I've done, and the reason why the training loop looks a little complicated, is what I've done is I've trained the model and I grabbed the output of the encoder directly, Z, right? So this is the output of the encoder. And then I grabbed the output of the quantized embeddings. And do you start to see some similarities here, right? So this is clearly a discrete representation, right? We have kind of these disparate points all spread out. right? These are the points that we have kind of all spread, and these are the only points I can take. On the other hand, the encoder, the neural network, right? The neural network encoder can output anything it wants, right? It can do anything it wants. It can spread around however it wants. It can do anything it wants to do. And there's no restriction on kind of what points it can take. But here, we're saying that you can only represent the latent space with just 512 codes. And the smaller you make your codebook size, the smaller basically the smaller representations that it can learn, right? The smaller places that it can learn. And so there we go. This is kind of the key idea. Kind of going forward, you'll kind of start to see, either way, there's not much of a difference here. I do want to give an idea of why we do the VQVAE. You can imagine that, for example, when we did the variational autoencoder, we saw that the outputs were kind of blurry, right? And the reason it's blurry is because the variational autoencoder learns both the kind of the data itself, like the different classes, the representations in the different classes of the data, but it also, because it forces it to be Gaussian, it also learns like an interpolation between the things. And what I mean by that is, let's say you're training a autoencoder on the cats and dogs data set, right? The VAE will learn both kind of information about the cats and information about the dogs, but it'll also learn the interpolation between dogs and cats. And you'll kind of learn like a half dog, half cat thing. That's not something we really care about. It doesn't make sense, right? And that typically leads to kind of a more blurry image because it's interpolating between the different classes that it's being trained on. The VQVAE, on the other hand, typically leads to slightly sharper images. And the main reason for that is because there's effectively a discrete latent space. The model can only map our data to one of many codes, right? So that code, first of all, has to be well representative of that sample. And this typically leads to sharper images because we're no longer interpolating between dogs and cats. You'd kind of just have like a group of points for the dogs and a group of points for the cats that kind of discretely represent those structures. You wouldn't have some like code that's trying to represent like a half dog, half cat thing. But either way, that's I digress, right? That is one of the key reasons we use the VQVAE. It typically leads to sharper images. And it's also really good for, feature extraction and stuff. And we'll see tons of applications of this when we start implementing more advanced speech architectures like the wave-to-vec architecture in the future. So let's go ahead and do one more example here. I want to do everything we just did, but for a convolutional vector quantized variational encoder, right? So you get an idea. Again, training these models are not that interesting, mainly because the training loop is exactly the same as before. So let's go ahead and let me move this back here. Okay, so how do we do this for a convolutional neural network? So same idea. Let's go ahead and do it. We're going to do class convolutional vector quantized VAE, right? And module def init, init self, and we're going to do in channels, right? MNIST has just one, so in channels is 1. Our latent dim is, let's just say 4. So this is going to be, we're going to compress down to 4 channels. Again, the code here is going to be almost identical to what we did before. So we're going to do, and then codebook size is 512. So I'm again going to copy everything that we've done before because there's no reason to type it. Okay. So just like before, we have a encoder, it's a stack of convolutions. We have a decoder, is a stack of convolutions, right? So nothing changed. This is exactly what we had before. And this should be 3 actually. There we go. Right? So exactly what we had before. And our bottleneck is in the number of channels, right? So we have bottleneck. And so all we've done is compress down to our bottleneck number of channels. And then our codebook is our codebook size by the latent dim, right? Whatever we used for the bottleneck. And so that's very simple setup. Let's go ahead and do everything else identically. So we're going to do def forward, and let's actually copy an example here. So we know our data is going to look like this. So let's just, right? So that's what our data looks like. Forward, self, x, and this is going to be our forward encoder, right? Our forward encoder, self, x. And let's comment u out for now because we haven't done that yet. And so our forward function is going to be exactly the same. we're just going to do our ConvEncoder. The encoder is going to be self.encoder conv(x). We're going to return conv(x). So there we go, nothing crazy. And then our quantization is going to be exactly the same, actually. Nothing changes. So we can go ahead and just copy our quantization function from earlier, right? So it's just going to be this again. Let's go ahead and copy it in. Right, so quantization didn't change, but there is one thing that did change, and this is how we do the quantization, and just something to keep in mind. In the case, and obviously you can do this however you want, right? It's completely up to you, but this is how it's typically done for like convolutional neural networks. In the MNIST example, right, let's kind of look here. We took our picture of a handwritten digit, right, and we compressed it down to some vector, right? And this vector was of some like latent dimension, and we picked 2, right? So let's do 2. And it was just one vector, right? One image, because first of all, we took this image here, right, of a 1 and flattened it into a long feature vector of size 784 by 1. And we compressed it down to basically 2 by 1 by using some linear layers. And then we went to the codebook and we replaced this with its code, right? And then the code went to the decoder, and that was it. But now we have an image and we're not flattening it. So the output of the encoder is going to be, right, when we do our encoder at the end, it's going to be some batch size by some channels, by some height, by some width, right? That's the typical output. And how do we quantize this? There's actually a couple ways you can do it, but the way we're going to do it is we're going to quantize every pixel individually. So what we're going to do is we're going to say that we're going to reshape this to batch size by height, by width, by channels, just like that. So there we go. And then we're going to flatten this to be batch times height times width by channels. So this is just going to be basically a long matrix like this, where this dimension here is going to be batch times height times width, right? That's going to be our flattened dimension, and then channel dimension here, or for embed. It's our latent space, right? Our latent dimension in our case. And we're going to, so that means this value, like this vector right here, is the first pixel, or basically the top left pixel, of the first image in this height and width across all the channels. So if we kind of look at a 3D representation, right? If we look at our, let's say this is our picture, right? Standard. So we have some height by width by channel. Ignore the batch dimension for now. What we're saying is we're going to take this pixel here and its entire kind of across all of the channels, right? Just like that. I guess I should draw this with a dotted line. We're going to take this entire kind of vector here of this pixel, basically all the numbers that represent this specific pixel. We're going to take all of them and quantize that. Quantize. Terrible. Okay, quantize. Let's just write Q. And then we're going to take the next pixel, right? So the one next to it. So that'll be this pixel. Again, we're going to quantize that. And we're going to keep going until we get to the bottom right. We're going to take this pixel, all of it, and we're going to quantize that. So we're going to quantize every pixel individually across all the channels. And this is kind of the standard way that we do it for, that I've seen it done for these convolutional neural networks. You could, of course, flatten your image, pass it through a couple linear layers, compress it further, and then do it there. But we're doing it this way today. So def forward decoder, self x. And what we're going to do is, first of all, our data, and this is going to, so x is already our compressed data, right? It's good. It's the decoded. And so what we're going to do is our batch size by channels by height by width is equal to x.shape. And let's go ahead and set this up. So first of all, we'll write the actual forward function, self x, and this is going to get our latent is equal to self.forward encoder x, and then we're going to pass into the decoder. Let's call this self.forward decoder. We're going to pass in our latents, or z, doesn't matter, And now we can run this, and let's get rid of, actually let's get rid of all that. Let's just do mrand. Looks like I missed a, oh, whoops, there we go. I missed a forward, there we go. So our latents, let's take a look. Print latents dot shape is a 2 by 4 by 4 by 4. So I've compressed my image down to a 4 channels, because I set the latent dimension, right? The latent channels as 4. So we have 4 channels, and then each channel is a 4 by 4. So what we're going to do is basically project each pixel individually across the channels. The other option could have been, I could have flattened all this, made it a 2 by 4 cubed vector, and then quantized those vectors of size 4 cubed individually. It's completely up to you, but this typically in convolutional neural networks, you're quantizing every pixel across the channels individually. So let's go ahead and do that. So first of all, we need to do our, let's go ahead and print it up here. So we're going to do print, same thing, x.shape. And then we're going to do x is equal to x.permute. And what did we want per mute? We want the batch dimension first, and then we want the height and width, and then the channel. So we're going to do 0, 2, 3, 1. In this case, it's hard to tell because they're all 4, but that's what we're doing. Right? Now this is going to be batch 0 by 2 height, 3 width, 1 channel. So the channel dimension is last. And now we're going to flatten it everywhere except for the last dimension. So we're going to do x is equal to torch.flatten. We can do x, and then you can specify actually the start dim is equal to 0. So I want you to start at the 0th dimension, the beginning, and I want you to flatten the 0th dimension, the first dimension, the 0th dimension, the first dimension, the second dimension, but leave alone the third dimension. So we can do start dim, 0, and then we can do end dim equals -2, so everything up to there. So then we can print x.shape, and we should see something by 4. We have 32 by 4, which makes sense. We had a batch size of 4, and then we had 4 by 4, right? So everything is, or sorry, batch size of 2, and then we had a 4 by 4, so that's 32 numbers. So we effectively have 32 pixels, and each pixel is represented by 4 numbers, right, along that channel dimension. So now's my opportunity to do the quantization. We can do codes, codebook loss, commitment loss is equal to self.quantize x. And the reason this is powerful, or more powerful than trying to quantify, instead of trying to create one big quantized thing about the entire picture, we create lots of different quantized things about different parts of the picture. And this allows the model to learn common pixel patterns that it'll find across different images, right? Like it can find, oh, like this pixel pattern is typically background, and it shows up in all sorts of images. So I can create a quantized embedding that goes with that pixel pattern specifically. And it's slightly more powerful in that way, rather than just creating one quantized embedding that's supposed to represent the entire picture, right? So it's basically more flexible. So we've done this, and now we can go ahead and do our codes is equal to, let's just put it back. So if we print our codes.shape, I must have misspelt something. Detach. There we go. I guess I spelled that wrong earlier too, so that's probably wrong right here. Detach. Right, there we go. We never actually ran it because we just tested it, but that's fine. Okay, so we have our codes.shape. And what we can do then is go ahead and put it back how we found it. So first of all, we're going to say codes is equal to codes.reshape, because again, we need to put it back in the image shape that we found it. So we can put it back in batch size by height, by width, by channels, right? Because we flattened these 3 dimensions earlier, so we're just pulling them back apart. And then we can do a dot permute, and we can say, again, batch should be first, then the channels should be second, and then the height and width. Codes.shape, just like that. So this is my quantized pixels, basically. And now that I've done that, I can pass my codes to the decoder. Our ConvDecoder is let's see, what did I call it? I called it the decoder conv, okay. Decoder conv codes. And we can go ahead and return our codes, our ConvDecoder, our codebook loss, and our commitment loss. So that's the key idea, right? So we have gone ahead and quantized it. And then we get our forward function. This is going to return all of this stuff for the decoder. And we can go ahead and return our latents, our quantized latents, our decoded, and our codebook loss, and our commitment loss, right? Okay, looks like I misspelled something. I just called them codes, okay. And then decoded is not, because this is called decoded. Okay, there we go, yeah. Okay, good. So that's again, just very simple setup. We could train this model. There's nothing fancy that you're going to learn here. Now the difference here is that we can't make a nice little visual because we have to like project it up, right? So we have to use t-SNE or something to actually visualize this. Just go take a look at my Git repo. I don't want to bother y'all with visualization code because this video's already gone on longer than I thought. So let's do a little bit of a recap, talk about a couple of problems, things we're going to talk about in the future, and we'll go from there. So again, as a recap, right, the VQVAE is basically just K-means, right? What we're trying to do is search for cluster centers that can represent our continuous data. We're mapping continuous data to these discrete cluster centers. And it leads to a couple of problems. Number one, that argmin operation that we do is not a differentiable operation. So to do that, we use the basically our pass-through gradients or straight-through gradient approximation, where we just pass our gradients from the decoder to the encoder, right? So it's nice and simple in that way. But if we're just copying gradients from one side to the other, that completely skips over the codebook, which means we still need to train the codebook. That part is still necessary. There's a couple of ways you can train the codebook, and the most common way is to use the commitment and the codebook loss, right? So again, where'd it go? The commitment and codebook loss functions right here, right? So our commitment and codebook loss basically just comes down to this, right? When we are trying to compute our commitment and codebook loss, the whole goal is we want to make sure the encoder, basically the trainable part, the encoder, is getting closer and closer to the codes themselves. And we want to make sure that the codes are moving closer and closer to the encoder output. But this both has to happen without ever computing a derivative between them. So you can basically imagine that in this codebook loss, these codes, which is coming from the codebook, right, our codebook, which are all trainable parameters, the codes are trying to get closer and closer to this target that's a constant. It's just a constant target that they're trying to move closer to. And in the same way, our neural network, which produces Z, is trying to get closer and closer to the codes, which is again now a constant target, right? Just a constant target for it to get closer and closer to. And this is just an approximation of trying to do an actual gradient. And then again, here's our pass-through gradient. Everything else is the same. And we didn't really bother training here. You can go to my Git repo and look at the training code. There's nothing fancy in there. I just mostly wanted to talk about the models today. But what are some next steps? So there's actually two things that I want to do with the VQVAE. The first one is I want to talk about the residual vector quantization, because as you can imagine, vector quantization, you're kind of restricted by a rounding error. For example, this center here, this cluster center here, is responsible for encoding all the information in the entire red box, which means even for stuff that's far away, it's still the point. And so there's a clear, there's a large amount of error between the true point and our cluster center we're using to represent it. And residual vector quantization uses multiple codebooks to try to solve that. So that's one thing we're going to look at. And that basically helps with the precision of our vector quantization. And we're going to need that especially when we do the encodec implementation for speech neural codecs that Facebook came up with. That's number one. The second thing we need to do is the Gumbel softmax quantization. So this entire getting around the min operation and all that stuff is non-differentiable. On the other hand, there is a distribution called the Gumbel distribution that comes from extreme value theory We'll do we'll actually do the derivation for the Gumbel distribution, I believe, if I can get around to it. But that distribution is a approximation of the max operation or the min operation. It doesn't matter, right? So it's an approximation of a max or min. And so if it's an approximation for something of something like max or min, then there's no reason we wouldn't be able to use it in our computation, right? We can replace it. And the cool thing is Gumbel softmax is a differentiable reparameterization of our min and max operations, essentially. So we're going to be taking a look at that too. Either way, I'm going to call it here. If you have any questions, go ahead and drop it down below, but I will see y'all in the next one.